now we will derive the expression for the discharge over a rectangular notch or weir. It is interesting to note that the expression for the discharge over a rectangular notch or weir is same. So you can see that in this particular figure, you can see here a notch and weir is shown. So on the left figure, you can see a notch is over there, and this is your crest and sill, which is shown at through this arrow. Over this water is flowing, and the top surface which is exposed to the atmospheric pressure, which is the nappe, and this right hand side, you can see that weir is over there. So this weir is working as a obstruction for any channel through which the water is flowing, and above the crest, water of height h at any location is flowing, and this h will be varying depending upon the position from the crest. So if we go for the derivation of the discharge over a rectangular notch or weir, and if we take any cross section, so the section at the crest will be drawn as a figure which is shown over there. You can see that this rectangular shape of the notch having a length of L. And if we talk about this section where the total head at the water over the crest, you can see this is the total head of the crest, okay, and L is your length of the notch and weir. And if we take any section of the width of DH, and this DH is such that this is located at a distance of a small h from the top surface. So if we take this particular strip which is shown over there, if we figure out the area of this strip, the area of this strip can be written as the smaller area. So area of a strip is, that is your L is your length, and the width of this strip is DH. So the total area of this strip can be written as DH. So however, we have to note it down that theoretical velocity of the water throwing so this strip is depending upon the head available to this one. So if we talk about the what is the velocity at this section, this theoretical velocity can be written as, so the theoretical velocity of the water flowing through this particular strip under the consideration can be written as under root 2gh. So h is the head above the head of the water above that particular strip. And if we consider that a discharge of a small so the discharge which is flowing through this particular strip can be written as dq. So this dq is can be written as the area of a strip multiplied by the theoretical velocity. So area of the strip, which is the consideration, multiplied by the theoretical velocity. So if we say that this theoretical velocity is Vt, so this is your Vt, and we are saying this area of a strip, that is a small area, so then let's say this is dA. So we can write that dq is dA multiplied by the theoretical velocity, that is Vt. Now in order to figure out the discharge or total discharge, we need to integrate this particular equation. So this total discharge, let's say this is q, so q will be the integration over this cross section, and that will give you the dA multiplied by Vt. Now there is a very important thing which is involved in this one. So total discharge, we have to integrate over the height of 0 to h, which is the height of the head over the Weir crest. So we can write that q is equal to integration over a height of 0 to capital H uh, dA multiplied by Vt. So dA can be written as, so the area dA is your length of the crest multiplied by the width under the consideration, that is L into dH, and theoretical velocity at this particular section is under root 2gh. Now if we integrate, we can just rearrange this equation. This can be written as 0 to h L under root 2g h raised to the power 1 by 2 dh. So once we integrate the above equation, this can be written as q is equal to L multiplied by under root 2g, and then the integration will look like h raised to the power 3 by 2 divided by 3 by 2, and the limits are 0 to h. So if we simplify this equation, this will look like q is equal to 2 by 3 L multiplied by under root 2g, and this is h raised to the power 3 by 2. So the equation of discharge we have find out is this one. However, this discharge we are getting is this theoretical discharge. So with the involvement of the channel and some very sharp opening, so the theoretical discharge we are getting will not be the actual discharge we will measure at the actual condition. So in order to assess the actual discharge, we do have a coefficient that is called as CD. This CD is the coefficient of discharge. And this coefficient of discharge, which is CD, is defined as the discharge we are getting in actual conditions, so Q actual divided by Q theoretical. So the above equation we have got the theoretical one. So in order to get the Q actual, we can write that CD multiplied by the Q theoretical, that is your Q. So the actual Q you are getting from the uh, rectangular Weir can be written as CD multiplied by the equation you got, that is your 2 by 3 into L multiplied by 2g h raised to the power 3 by 2. So the final equation you are getting is like this one. Usually the values of CD are usually in the range of 0.58 to 0.62 for such VS. Take a numerical problem to figure out the discharge of the water over a rectangular notch. So the problem says that find the discharge of the water flowing over a rectangular notch of 5-meter length when the constant head over the notch is 500 meter, and we have to take the CD value is equal to 0.6. So before starting the solution, we should first of all note down what the values which are given to us. So the length of notch that is given to us, that L is equal to 5 meter, and head over the notch or crest, or the crest of the notch is 500 mm, so that is 0.5 meter, and CD value is also given to us, that is 0.5, sorry, this is 0.6, 0.6 So the expression we will use to solve this problem is Q is equal to 2 by 3 CD multiplied by L multiplied by under root 2G H raised to the power 3 by 2. So this is 2 by 3, 0.6 multiplied by L is 5 multiplied by under root 2G, that is 9.81 multiplied by H is 0.5 raised to the power 3 by 2. So if we solve, this answer comes out to be 3.148 meter cube per second. That is the our answer. So the problem says that head of the water over a rectangular notch is 1800 mm, discharge is 1000 liters per second. Find the length of the notch when CD is equal to 0.6. So let's start for the solution. So the given values are H, that is 1.8 meter, and Q is 10,000 meter cube per second. Sorry, this is liter per second. So this value will be 10 meter cube per second. So here one important thing you can note down for your is that 1 cubic meter equals to 1000 liter. Now another thing that is given to us, that is CD, that is 0.6. So we have to determine the what is the length of the crest. So we will again use the same equation, that is Q is equal to 2 by 3 CD multiplied by L under root 2 G H raised to the power 3 by 2. So Q is your 10 multiplied by 2 by 3, CD is 0.6, L multiplied by 2, 9.81 multiplied by 1.8 raised to the power 3 by 2. So L is coming out to be 2.3255 meter. However, the preferable answers should be in the 2 digits, because this is the length of the crest. So you can write that this is 2.33 meters. So that is your answer. The length of the crest is this one. So you need to remember this thing. There are one variable, second variable, and the third variable. So out of three variables, two will be known to us, and third we have to derive. The only purpose for solving all the three types of problem which is shown over here is that if you keep on writing the formulas by your own self and just putting all the values 2-3 times, so it will be easy for you to remember the formulas. So that's how you will not make any mistake while attempting any similar kind of problem in your examinations.